There are countless videos on YouTube in which experienced photographers dissuade newcomers from shooting at small apertures like f16 or f22. Especially in landscape community, it is considered a big no-no for a long time. In this video, I'll try to dive deep into the topic of diffraction, an effect which supposedly becomes apparent at these apertures in photography. We'll discuss the nature of it, an impact which it has in our photos, and also conduct some tests to see whether we should be bothered by this. We'll also try to explore a lesser known territory, how to use diffraction creatively. Firstly, what is diffraction? It is an effect which occurs when a wave of any kind bends around obstacles. The easiest example is an ocean wave bending around a breakwater. Water then becomes messy and distorted and eventually changes its form. For us people, it's one of the methods of controlling nature and avoid floods and infrastructural destructions during storms. As we all know from the school program, light also bears the properties of an electromagnetic wave. So diffraction occurs when a beam of light meets an obstacle on the verge of which it still can pass. Basically, light passes through a hole. Considering the fact that all our world consists of holes and light, diffraction happens pretty much everywhere. Here, everyone usually refers to Huygens principle. According to this principle, every point on the front of the light wave, which is the imaginary line at the front end of the wave, can be seen as the source of new smaller spherical waves. And everything what I said is probably very difficult to understand verbally, but might turn out actually pretty straightforward while using simulations. So this is an array of coherent light sources, our imaginary camera sensor and a slit in between them, which will represent our aperture. If we measure brightness in the different parts of our receiving sensor, we'll get a graph like this. But what if we make a hole smaller? Let's observe what happens. Let's make a hole even smaller and measure brightness again. We now see that graph becomes less dynamic, much less resolving, it has less peaks and it is smoother. That represents both fall of the brightness and resolving power, and it's an effect which we can see in our photographs. Everything becomes smoother, contrast and details are lost. For a very accurate and scientific interpretation of diffraction, I highly recommend you to visit a channel which is called Huygens Optics. There, all the physical formula is described in a way even us mere mortals can understand. In short, bigger the hole always equals more theoretical resolution of an image, which is formed by a wave even if we are not introducing any optics in the system yet. Here is very unscientific and fundamentally wrong but effective example I came up with. Imagine a sea which is going to represent our optical path. The light which comes through the lens is the water, and its shores are the physical barrel of our lens. When the wind occurs, waves form, thus our hypothetical light shines. After some time, waves reach the shores. What happens? Some of the water spills onto the ground, some reflects back to the sea and muddy the pattern a bit. Let's say our waves are 30 centimeters tall. In the scale of the sea, it doesn't change much. We'll still see relatively calm and predictable pattern of waves. Thus, we'll see a clear image projected by these waves. But what if our sea becomes the puddle? Puddle is our smaller lens. If the waves of 30 centimeters are introduced in the puddle, there shortly will be no puddle left. This will be totally chaotic water system, and the image projected by the waves will, in fact, be much muddier. In the image, it will be seen as blurring of details. So in this scenario, the main factor for the clarity of the picture we see will be the size of a water body, or an aperture of a lens. This is obviously true for photographic lens. Diffraction occurs at all effective apertures, but the bigger the hole, lesser the f number, lesser the effects of it are. Sadly, our optical systems are not perfect. Most of the existing lenses are poor performers wide open due to several reasons, which we are not going to discuss today. Also, depth of field, which is greatly needed in landscape or macro photography, becomes thinner on wider apertures, so we naturally stop the lens down. But what else, except for physical aperture size, is affecting diffraction? There are actually a few other variables, but firstly, let's discuss what doesn't. The focal length of a lens doesn't affect the diffraction, which visually is actually quite counterintuitive. Look at the physical size of an effective aperture f5.6 on my 30mm Tair 3 lens, and look at the same size of the very same effective aperture on my tiny 50mm Industar 52. Clearly Tair's is bigger, thus it should give a better resolving power. But in camera lens, f number, which we all are accustomed to, is a relative measure, not absolute physical one. It shows relation of a focal length to the diameter of an entrance pupil, which in the most optical systems is a virtual plane and lies behind the first element of the optical system. It determines the size of the cone of rays which optical system will transfer. The point is, you cannot really measure it yourself, but the optical engineers of a lens did it for you. So not only size of a hole goes into equation, but also some other inherent optical details which we, as photographers, don't always know. What is also important is the distance from image plane. Every lens in the world has a built-in mechanism of moving everything in and out. It is called focus. When it is close, our camera is focused on infinity. When we move our lens block away, we focus closer. That's also how extension rings work, distancing lens further from the focal plane. When the lens is extended far away from the perspective of image plane, relative size of a hole becomes smaller. Does it mean that diffraction effects will be stronger on closer focus distances? Yes, it does. Everyone who tried serious macro at least once in their lifetime knows that most of lenses degrade in close focus situations. Closer the focus, worse the quality of an image will be. This is also why most modern macro photographers shoot near open and then stack thousands of differently focused images later in Photoshop instead of simply closing down the aperture. While shooting extreme macro, even f8 can turn into effective f45 because the lens is so far away from the focal plane and the aperture hole appears so small. That is also why image in close focus appears dimmer. It is because it is. With greater distance, less light falls on image plane. Try standing near illuminated window at night. At 1 meter, your pupil will constrict, as there will be a lot of light coming into your eye. But at 100 meters, much less light will enter your eye. Large format shooters are very familiar with this problem. When they shoot something from a short distance, they calculate the bellows factor. As the bellows expand, focus gets closer, but the light reaching the film spreads out, reducing brightness. This means, when shooting macro, exposure compensation is necessary to maintain proper image brightness. And this is a great place to think of how sensor size affects diffraction. On the same f-stop number, which we know now is a relative number, every lens produces the same physical apparent size of diffraction, like blurring of an image, onto a focal plane. Thus, theoretically, diffraction doesn't depend on sensor size. But we always observe images enlarged. Let's say my laptop screen is 36 centimeters wide. If I observe an image gotten from full-frame digital sensor or a film at a full screen, it will be enlarged 10 times, as width of a full-frame format is 36 millimeters. If I produce an image with 6x8 medium format camera on the very same screen, it will be enlarged only roughly 4.5 times, as actual negative will be 77mm size. And if I shoot something with 8x10 camera, I'll hardly need any enlargement at all. Let's conclude. The more you enlarge, the more effect of the diffraction will be enlarged. Thus, shots which were obtained with smaller formats like APS-C or Micro Four Thirds, while viewing, will show more diffraction than larger formats. One more thing to consider when thinking of diffraction is your camera's megapixel count. If we take two full-frame cameras, one with a smaller megapixel count, let's say Sony a7S III, which bears 12 megapixel sensors, and Sony a7R V, which bears 16 megapixel sensor, latter one will show significantly more diffraction. Let me show an effect which basically is a visualization of diffraction, and it's called airy disk. Because of diffraction, a single dot of light on a dark background, let's say a star in the night sky, in higher magnifications resolve not as a dot, but as a concentric planetary circle. Airy disk show the very waves of light which pass through our lens or a telescope and bump into the walls of an optical path, creating these interference patterns which are muddying the water. And all the points of light you can imagine every second create these tiny airy disks at different wavelengths, and it all goes to a sensor. Higher megapixel cameras obviously have a smaller pixel size, as you need to stuff more pixels into the same area. For a7S III camera it will be 8.4 microns. For a7R V it will be mere 3.7 microns. If an airy disk of your optical system can fully fit into one pixel, Well, you didn't muddy the water much. Your camera has lower resolution than your aperture. But if your airy discs fall onto several megapixels, then it will muddy the water much more. Here I need to point out that it is not really about what is sharper, lower or higher megapixel cameras, because your resolution will be limited no matter what, either by diffraction or by small pixel count. But optically, lower megapixel cameras will be better performance when stopped down. For them, at higher enlargements, it will just be not soft, but pixelated. And the next thing which I want to discuss is something no one really seems to talk about. Probably because this topic is much less practical, though I tend to disagree. You see, diffraction is dependent not only on aperture size, but also on the wavelength. Literally, the length of a wave. Imagine the same puddle, but instead of 30 cm waves, there will be 2 cm waves. Much more manageable, thus image will theoretically be clearer. Human vision can observe wavelengths roughly from 380 to 700 nanometers, but there are much more electromagnetic waves in specters. Radio waves, for example, can be very big, up to tens of kilometers in size. That's why radio telescopes are so big. Their long waves generate very large diffraction patterns, so high resolution can only be obtained using big apertures, sometimes covering the entire Earth, as it was the case with the Event Horizon telescope, which first captured the black hole. The observing wavelength was gigantic 1.3 mm, which is 2600 times longer than the wave of a visual light. What does it mean for us as photographers? It means that shooting at shorter wavelength, which is blue spectra, will theoretically make diffraction effects a bit smaller. We can do it in two ways. Either we carry UV lamp with us at all sets, which is not only highly inconvenient, but I suspect highly illegal and dangerous, or we use blue filter. And I love blue filter. I think it's one of the most underappreciated tools in the photography, as everyone uses this dark red and orange for dramatic skies, but blue one, I'll make another video on it, I promise. So let's conduct an experiment. We'll create some extreme conditions where the lens will be visibly diffraction limited by shooting in the macro range. We'll do it with two color filters I have, red and blue, and see whether it makes any difference. We're placing our subject at the closest possible distance with the set of macro rings. Our aperture is f16 and our effective aperture will roughly be f30. I don't know whether this is apparent with YouTube video compression or not, but I'm surprised to see that the difference between the two is actually quite noticeable. So blue wave is approximately 2 times shorter than the red one, thus difference in diffraction should resemble roughly one stop of an aperture. And if you look very closely at finest dust particles, we'll see that they are indeed softer in the red one. Contrast is also much lower, but I suspect it happens not because of diffraction, but because of my lighting conditions and a warm flare created by reflections in badly blackened macro rings. Blue filter blocks it, while red filter enhances it. Consequently, we have another discovery. Orthochromatic films and papers, which are made to this day, will exhibit more sharpness while stopped down, as they're mostly sensitive to blue spectrum and don't really react to warmer light. So, okay, this was all theory. What can or should we do with diffraction in practice? Here I share my personal experience, and if you don't agree with me or just have something to say, please let me know in the comments. Firstly, basic logic tells us that diffraction should behave more or less the same on different lenses if f-stop number is the same, so the relative aperture will be the same. In practice, I found that diffraction is perceived somewhat differently on different glass, and I suspect lots of it doesn't really have anything common with diffraction as is. For example, on my Mir 1B, which is overall very poor performer, at f16 image worsens dramatically. Here you can observe huge loss of a contrast and some loss of sharpness. From the other hand, on my modern RF 24-50, which I consider one of the very worst lenses ever produced, both mechanically and optically, worsening of an image is much less pronounced. Details start to break apart only at f32, but even at this extreme aperture, the image is consistent with contrast and possesses no additional artifacts. So, in my opinion, final image remains quite manageable. My InDestar 52 slightly worsens at f16 and the most apparent effect is loss of contrast, whereas details are generally preserved. From the other hand, my Jupiter 21M doesn't break even at its smallest aperture, f22, and possesses no visible contrast or detail loss on a 24 megapixel sensor camera. So, as you might see, there is no apparent logic for us as photographers. We just need to go out and test it, as there are plenty of other factors in this equation of a quality sharp image, such as coatings, collimation of lens, inner reflections, etc. Also, in my opinion, the problem of diffraction is greatly exaggerated by YouTube and forum influencers in order to gain views. Whereas what they say is technically true, in real-life situations it matters very little, even for photographers with the highest printing demands. Except from Mir 1B, all my other 15 lenses, vintage and modern ones, at least on 24 megapixel full-frame sensor, degrade very little at closed apertures. The only field where diffraction becomes ultra-critical is macro work. Here, closed apertures lead to significant degradation of an image, but if you do macro, you probably already knew that. If it comes to landscape photography, I am all for focus stacking if needed, but it shouldn't discourage you from using small apertures when there is simply no other way. For example, if you don't have a tripod for these series of static shots, or you're in a huge hurry. Also, in my opinion, even if you're a huge pixel peeper, as most of landscape photographers are, you don't need to pursue bigger pixels just to avoid diffraction. In the end, ultimate resolving power will still be limited one way or another. And I never seen a single picture ruined by the diffraction. Poor lighting, poor composing, veiling, blooming, chromatic aberrations, inadequate depth of field, yep, seen those. But diffraction? Never. And to prove or disprove my point, I'll conduct another experiment. This is InDestar 11, a Tessar-type large format lens with 450mm of focal length and aperture which starts from f9 and ends on f90. Comparing with full frame, it will behave roughly like 58mm f1.1 lens. We'll shoot the same scene with f22, which is considered a standard landscape aperture in large format world, and whooping f90 to see the differences ourselves. So we are in the Petrovsko-Razumovskaya estate, one of the oldest Moscow palaces. It was built around the middle of 18th century in the French style. I came here with large format camera and will make two shots. First one at f22 and our exposure time will be 64 seconds, second one will be shot at f90 and corresponding exposure time will be 18 minutes, we'll round it up to 20 minutes. It is very dark here and I'm also shooting paper negatives at ISO 3, so let's go. Clearly I did something wrong in the development stage, so sorry for gnarly looking negatives. For our testing purposes, it will be okay. At low magnifications, I see no visible differences in detail, and I also couldn't see them while observing the actual negative. In high magnifications, though, first picture is clearly perceived as more detailed. Remember that these are quite small parts of a negative. Anyway, differences of 4 stops is apparent on 50 megapixel scan, but not destructive. You might say, Vlad, it's an 8x10 camera, of course diffraction will be less obvious in these larger formats. Try shooting f90 at 35mm or smaller. To this I say, 35mm lenses can't reach f90 anyway. Most of them are limited at f16 or in some cases at f22 or f32. So still no real point on worrying on diffraction effects. In the end of a practical part, I want to present you a short list composed in the following order. From those who should care about diffraction the least, to those from who it might actually become a problem. 35mm and 120 film shooters. I am absolutely sure that casual film shooters, even landscape pixel peeping many square meters printing one, should not care about the diffraction. I shot at apertures from f16 to f22 in full frame and a medium format a lot of times, and was never bothered by diffraction. I think it is because generally 35mm film, while being also medium, generally can't resolve like 60 megapixels, where diffraction can become a problem. And 120 format definitely can do that, but because the medium is larger, diffraction affects final images much less. Large format shooters. Your pictures are very rarely greatly enlarged, so no point on worrying on diffraction effects also. Full frame digital shooters except macro. Actually, no one really cares of slight resolution fall-off on the veins, of the leaves, of a beautiful tree you shoot from 50 meters with your bazillion pixel camera. APS-C sized large megapixel digital shooters. Here, diffraction can actually start to bother you a bit in the most extreme situations. I would avoid going past f16, though f16, I think, will be absolutely fine in most cases. Micro Four Thirds and smaller sensors. Here, perceived effects of diffraction can be exponentially more pronounced. But you rarely shoot fully close, since depth of field of a typical Micro Four Thirds lens is so big anyway, and there are problems with noise and glass is good, might as well shoot anything at f5.6. Macro shooters of all formats. You generally tend to know what you're doing in terms of diffraction, so I won't give you any advice. But quite obviously, in your work, diffraction is huge pain in the ass, and your whole process is built around it. Last part of our video will be dedicated to creative use of diffraction. There is one particular genre of photography, which aesthetics are based solely on diffracted look. And one might say this genre precedes photography itself. I'm talking, of course, about pinhole photography. As you already know, there is no lens in pinhole camera, only a small hole through which the image projects itself onto an image plane. As there is no glass or mirrors which distort and reflect light, pinhole image is optically perfect. It is free from any aberrations you can imagine. Chromatic aberrations, astigmatism, coma, etc. It also has an infinite depth of field, no blur or bokeh. There is only a vignette, for the reasons we won't dive deep today, and diffraction, which gives pinhole images this signature soft and mellow look. Starting from the certain diameter, smaller the pinhole, softer the picture will be. Unlike lens photography, here diffraction actually depends on focal length, as focal length of a pinhole system is literally the distance between the hole and the focal plane. So as the hole is placed further, effective aperture decreases. So pinhole enthusiasts calculated a formula for the perfect hole size for different focal lengths. If you want, you can find these calculations online. And yes, an impact which hole size have on a final shot is very huge and very noticeable. But diffraction can be explored not only in these unorthodox scenarios, but also using more generic gear. So I really like my half-frame film camera. It's Chaika 2. And it has beautiful little lens. 28mm f2.8 Tesseract style pancake. And once upon a time, I was shooting it with infrared filter at very closed apertures. And I noticed some very peculiar characteristics with images obtained. They were a bit soft, but not usual soft, rather pleasant and lo-fi, but still kinda sharp soft. And only in the process of making this video, I realized that I basically fulfill most of the conditions for diffraction to appear. It is a very small format, very long infrared wavelengths of light, which theoretically should be affected by diffraction more, and also closed apertures. To be fair with you, I'm still not exactly sure whether it was diffraction mixed with some grainy film or something else. But industers, and this lens in particular, are generally known to be sharp, especially in closed aperture situations, so as for now, I'll think that it's a diffraction. Also, there is an interesting effect on which Steve O'Nians, one of the very best photographers on YouTube, likes to talk. You see, Micro Four Thirds sensors have some kind of soft filmic look to it. And partly it's, of course, because pixels are smaller, so you get more noise and grit in your images. But might this also be because of a more pronounced effects of diffraction? Since Micro Four Thirds and half frame are equal in size, probably we were observing the same effect? Anyway, that's pretty much all I wanted to yap about within the topic of photographic diffraction. As usual, if you have something to say, or if you want to correct my mistakes, which I'm sure there are plenty of here, please write it down in the comments. I'm answering everyone, and for now, I'll bid you farewell.